cohomological, McKay correspondence via Floer theory.
Does it work? Yeah. Oh, excellent. So thank you so much, Leonardo, for this invitation, and thank you to the organizing committee. It's a real pleasure to be back in IMPA. I still have fond memories of the workshop from 2011. So all of what I'm going to say is joint work with Mark McLean, and I'll be talking about the generalized McKay correspondence. So let me start off with the big picture. So what we're doing is we're studying resolutions of quotient singularities. So what this means is we look at complex space Cn, and we look at a finite subgroup of SLN, and we quotient by this group action. So this is an affine algebraic variety, which is singular. The singularities are the singular points of this variety are exactly vectors that are fixed by some non-identity element of G. So they are the one eigenspaces of non-identity elements. So the space is certainly singular at the origin, and then it can have these singularities along vector subspaces, so that the singular strata go off to infinity. And what one does is one wants to replace this by a nicer space called a resolution of singularities. So resolution of singularities means that you modify your singular space exactly where it is singular at the cost of creating more topological invariance. So Y has a much richer topology than X does, but the benefit is that Y is now smooth. And you've only modified X where it was singular. So the formal definition is, for our setup, resolution of singularities means that it's a non-singular quasi-projective variety. The map pi, the projection, is a proper birational morphism, and it's an isomorphism away from the singular locus, so away from the exceptional locus, which is over the singular strata. And the motivating question in a lot of algebraic geometry literature is, can you relate the geometry of your resolution of singularities Y to some invariance of your original space and how it was created? So in this case, how this is related to the representation theory of your original group G. Okay, so this is the general story. So let's start off with the simplest possible example, which is the A1 singularity. So here our group is just Z2, so Z. Acting by plus or minus 1 on C2. So we have C2 modulo plus or minus the identity. And we view this affine variety, we can embed this into C3 the following way. So here we have coordinates X and Y. We embed this by looking at which polynomials in X and Y are invariant in this group action. So X squared is invariant, Y squared is invariant, and XY is invariant. And now let's call these coordinates capital X, capital Y, capital Z. So the image of this variety is given by X times Z equals Y squared. So what this is the real picture of this is a double cone with and there's an isolated singularity at the origin. And this is the real picture of this. So far we've done nothing. This is still the same variety. This image variety is still the same as the original variety. And in order to produce a resolution of singularities, you try to blow up the singular strata. So in this case, we blow up C3 at the origin. And what this does is it replaces the singular point by a copy of CP1. So in the real picture, this looks like a circle. Okay, so this is pi. This is the space. This is the space X and Y. So here, I apologize for the mental gymnastics that this X is not the same as the coordinate X. Okay, so now the big picture question was: is the geometry of the resolution related to the representation theory of G? In this case, the topological invariance we look at of the resolution is the cohomology. So this space here turns out to be the same as the cotangent bundle of CP1. So the cohomology of this is just the cohomology of CP1. It has two generators. And the fact that it has these two generators, the constant function 1 and the Kähler form, the fact that it has this vector space is two-dimensional is related to the fact that there are exactly two irreducible representations of the group Z mod 2, which are the silly representation, the trivial representation, and then the representation that acts by plus or minus 1 on C. Okay, now I won't say much about this is the two-dimensional case, so that when n is 2, I won't say too much about it. Just one slide, because it's such a beautiful classical story. So this is called the classical McKay correspondence. In this case, basically everything is known. So in this case, the finite subgroups of SL2 are classified up to conjugation. They are just cyclic groups, the dihedral groups, and then the groups of symmetries of the Platonic solids. So the tetrahedral group, octahedral group, and icosahedral group. And then these little twiddles, they double the size of the group. That's because you think of these groups first as rigid motions in R3, so subgroups of SO3, and then you lift them by the double cover to SU2, and so then they give you subgroups of SL2. Okay, and the classical story is that these all these groups are in one-to-one correspondence with ADE Dynkin diagrams. So this story that we had here generalizes. So what you do is you look at the invariant polynomials in X and Y under this group action G, and it turns out that the ring of invariant functions, invariant polynomials, is generated by three polynomials, just like these three, and they give you an embedding into C3, and this has an isolated singularity at 0, and in fact this is another nice story in singularity theory, which is that they classify what are called the simple surface singularities. So they were studied by Klein and then classified in 1934 by Duval. And they're also called rational double points. And so here's another sort of a slightly more complicated picture than this. This is the case of the quaternion group of size 8. And then you get some equation like this in C3. You try to find the smallest possible resolution, so you blow up as few times as possible. And what it does, it replaces this isolated singular point 0 by a tree of copies of CP1. So this is the real pictures. They look like circles. And this tree of copies of CP1, they are arranged exactly by a Dynkin diagram. And then this classical theory tells you that actually the Dynkin diagram remembers everything about your original group G. So this is perfectly shows that this resolution remembers everything about the group. So the general statement of the classical McKay correspondence is that minimal resolutions of these quotient singularities, over the singular point, they have a tree of copies of CP1, the exceptional divisors, and these are in one-to-one correspondence with the non-trivial irreducible representations of the group G. Okay, and I'll just make two quick remarks. One is about the homology, or if you like, cohomology. These exceptional divisors, these copies of CP1, they generate the cohomology together with the constant function in degree 0. And another brief remark, because later I'll be speaking all the time about conjugacy classes. I'll just make the remark that for finite groups, the number of irreducible representations is exactly the number of conjugacy classes. So later on, I'll stop speaking about irreducible representations, because if you just want to count them, it's the same as the number of conjugacy classes. Okay, and there's not enough space on the slide to mention the vast literature on this topic, so I'll just mention three important papers in this area. One is the original paper by McKay from 1980, which tells you that from the extended version of the Dynkin diagram, you can basically read off everything about the group, in particular what's called the McKay quiver for the standard representation C2 is exactly this, the Dynkin diagram. And this statement about number of irreducible representations and irreducible representations and generators of the cohomologies can be generalized to a statement about decay theory. So in 83, Gonzalez, Sprinberg, and Verdier showed that the K-theory of the minimal resolution actually recovers the representation ring of G. And then this can be further generalized. Instead of studying vector bundles, you can study coherent sheaves, and you get a statement about the derived category of coherent sheaves on the minimal resolution. And again, just like the sort of the motto here is that you want to recover information from about Y from the information downstairs, you recover the derived category of coherent sheaves on the minimal resolution from studying the derived category of G-equivariant coherent sheaves on C2. This is by Kapranov and Vasserot. Okay, so that's all I'll say about the dimension 2 case. So in the higher dimensional case, life is harder, as it usually is. And in this case, one of the first problems that you encounter is that there's no clear notion of what the best resolution should be. So in a two-dimensional case, you have these minimal resolutions. That means any resolution has to factor through this minimal one. So there's a preferential one, and it's unique up to isomorphism. But already in dimension 3, one problem you encounter is that minimal resolutions are not unique. They are related by flops. And then in higher dimensions, there's no good notion of minimal resolutions. They sometimes don't exist. And so what you would like is but you definitely need some sort of statement, some sort of minimality statement for your resolution, because even in this two-dimensional case, if I just take a point in the exceptional divisor, blow it up, I can create more cohomology. But it's still a resolution of your singularity. So you can increase the cohomology arbitrarily and while still having resolution. So you need some notion of minimality for the resolution. And this notion is due to Miles Reed, and it says that what you should be looking at is crepant resolutions. So a crepant resolution means that the canonical divisor downstairs on Cn mod G lifts precisely to the canonical divisor on Y. So for these nice singularities, the general statement is that your canonical divisor on Y is the pullback of the canonical divisor together with a non-negative sum of all the non-equivalent exceptional divisors that you have upstairs. So the fact that these exceptional divisors come with positive non-negative coefficients is due to the fact that this is a nice singularity, a very nice singularity. The ones that arise with coefficient 0, so the ones that don't arise in this equation, they're called the crepant divisors, and it's a result due to Ito and Reed from '94 that those crepant divisors actually have to arise on every crepant resolution. So that's already a good sign, because it tells you that even though you might have many different crepant resolutions, they all have in common these special divisors called the crepant divisors. The fact that they arise is because they are classified by the function field of Y, which is the same as the function field of X. Whereas these exceptional divisors that arise with strictly positive coefficients, they form what's called a discrepancy of the resolution. And so Miles Reed coined the term that if you don't have discrepancy, then you are crepant. Okay, so this is the good notion of resolution. And I should say that just like in the case of the minimal resolutions, these resolutions, they don't always exist. And even when they exist, they are typically not unique. Okay, so where the story is sort of generalized, this is due to string theorists, Dixon, Harvey, Waffe, and Witten from '85, and then later work by T.S. Siegel and Hirzebruch-Hoefer. They conjecture that for a crepant resolution, the Euler characteristic should recover the number of conjugacy classes. So in other words, the number of irreducible representations of the group G. And Miles Reed then refined this statement by saying exactly what the Betti numbers are of the crepant resolution. So first of all, the crepant resolutions have no odd cohomology. So here we're always working over complex coefficients, has no odd cohomology. And the even cohomology, the rank of the even cohomology is precisely a count of conjugacy classes with a specific grading. And this grading is called the age grading. So I'll tell you now what this age grading is. So the age grading is, if you give me an element of SLN, for some technical reasons you look at the inverse, but you can ignore that technicality. So you've got this matrix in SLN acting on Cn, It has finite order. Its eigenvalues are roots of unity. And you can write these roots of unity by uniquely if you specify that you want your phases, these angles, to be between 0 and strict 2 pi. You add up all these angles, so you sort of average these angles and divide by 2 pi, and this gives you a number called the age of this element G. And just let's do a sanity check here. The Y is a non-compact manifold. The cohomology should be supported between degree 0 and 2n minus 1. And this average of these angles lies between 0 and strict n. And so when you double it, indeed, these numbers are between 0 and 2n minus 1. And another sanity check is you might ask, why is this an integer? Well, because these elements G are in SLN, the determinant is 1. The determinant is the product of the eigenvalues. And so the sum of these phases has to be an integer multiple of 2 pi. So again, that's another sanity check that this is really an integer, as it better be. Okay, so so what's known about this is that this was proved by algebraic geometry methods in dimension 3 by Ito and Reed in 94. The dimension 2 case was classical, of course. Dimension 3 by Ito and Reed in 94. For abelian groups G, as we heard by Miguel, this was proved by Batoréo and Dias in 96. And then this was proved in general by Batoréo in 99 and Denef-Leuser in 2002 using Koncevich's motivic integration machinery. So pretty high-tech techniques on the algebraic geometry side. Again, the slide is too small for mentioning all the literature that was developed in the last 20 years in algebraic geometry on this. I'll just mention a few names here. The work of Ito Nakamura, Ito Nakajima. So a lot of this work is about actually asking the question, how do you actually build Krepin resolutions, which is a hard problem. And there's a model called the G-Hilbert scheme. But it's a sort of hard problem to decide when there's a Krepin resolution and how do you actually build it and how are they related. And then another sort of generalization of this result by Kapranov and Vasserot about the derived category coherent sheaves. This was generalized to dimension 3 by this, in this famous JAMS paper by Bridgeland, King, and Reed in 2001. Now, it's still these proofs, they still are somewhat mysterious why these numbers are actually the same. And maybe to justify why it's just that I say that it's mysterious, it's an open problem in the algebraic geometry literature is still, can you actually find a natural basis for the cohomology of the Krepin resolution in terms of the conjugacy classes? So if I give you a conjugacy class of G, what cohomology class should that correspond to? And there's no sort of natural question. In fact, even the word natural is also a bit ambiguous. A famous paper in this direction is the Invenciones paper by Keledin, which says that if you assume in addition that your finite subgroup of SLN, in this case n, you require n to be even, 2m. If you require that your group preserves the complex symplectic form on C2m, then in fact you can produce a very natural basis that proves this cohomological McKay correspondence using a method involving what are called valuations. Okay, so there's not all that much work that has been done in the symplectic literature on this, and part of the issue is that the dimension 2 case has been studied a lot because those are smoothable isolated singularities. So they're the famous asymptotically locally Euclidean spaces studied by Hitchen in 79 and then Kronhammer in 89. And they have a very nice hyperkähler description. You can deform these singularities in families into hyperkähler manifolds, and they have exact symplectic forms, and the Floer theory is very nice. But in higher dimensions, these Krepin resolutions are non-exact symplectic manifolds. Already for isolated singularities Cn mod G, these singularities are not smoothable. This is due to Schlesinger's rigidity theorem. So it's sort of slightly outside of the technical realm of symplectic topology because you're working with these non-exact symplectic manifolds. But I'll mention two works in this area. One is by Joe Nelson and other authors in 2015. They looked at this two-dimensional case, the AN surface singularity, and they described the explicit generators of something I'll mention later, and that we also heard in the previous talk, this S1 equivariant positive symplectic cohomology. I sort of wrote down explicit orbits and calculated the Condy-Zender indices and show that there are exactly n plus one generators in this Floer group. And again, according to our motto, we expect that invariance of Y should be related to the original group G, and indeed, these Floer invariants of the resolution then recover exactly the number of conjugacy classes of the group that's involved in this case, in the AN case, which is Z mod n plus 1. And another result is by Miguel and Leonardo from 2016, which we heard of mentioned before, which is if you're working in this in the Batoréo case, in the abelian case, or the toric case, and you have an isolated singularity, then you can look at the generators of the linearized contact homology, and you calculate this mean Euler characteristic of the contact manifold, so the link of the singularity, and again this recovers this again recovers the Euler characteristic of the Crepin resolution. Okay, and so the talk today is about the following theorem, which is so we're going to study the case of any finite subgroup of SLN, but assuming that the singularity is isolated. So we assume that we're given a Crepin resolution, and we claim that we can build a bijection. So this is the McKay correspondence. We can build a bijection from the conjugacy classes to a basis of the cohomology using Floer theory methods. Okay, so here maybe I should mention an interlude, which is, to some extent you might say, why do you want to reprove this? Why do you want to reprove the McKay correspondence if algebraic geometers have already proved it? And so here my best line of defense is to quote a famous Italian mathematician called Giancarlo Rota, who was at MIT, and he wrote this nice book called Indiscrete Thoughts. And he said mathematicians come in two categories: the theorem provers and the theorizers. So for the theorem provers, mathematics is a sequence of challenges to be met, and he said, and it's an obstacle course of problems. And so if you're that sort of mathematician, this was the obstacle that has been overcome, and that's the end of the story, and I should stop speaking. Then there's the theorizers, for which he said achievements in mathematics is to develop a theory that sheds sudden light on some incomprehensible phenomenon. And so my hope is that at least to some extent what we hope to do is, by giving a symplectic proof of this cohomological McKay correspondence, we're hoping to shed some new light on why this statement should be true. So actually our hope is to prove this open problem, that there's a natural basis, and we sort of got part of the way, but not quite all the way. Sorry? Yeah, so we haven't a statement of that type, but I'll explain what I mean by naturality for the purpose of this talk in a second. Okay. And so here I'll just mention two small things. This fact that the singularity is isolated, that's equivalent to saying that you want the group G to act freely away from 0. So that means that there's no eigenvectors with eigenvalue 1. And we're currently writing up the work in a non-isolated case, which is quite a bit trickier. There's some Floer theory problems to be solved in that case, but it basically builds on this work. I'll also only make a very brief remark about the field. The talk will talk about the characteristic 0 case, but you can also work with fields of finite characteristic, provided you avoid low values of the characteristic below the size of the group to avoid torsion phenomena. But another question that we're interested in is to think at some point about torsion phenomena in the statement, and in particular in the Floer theory. Okay, so before I get into the technical details, let me just say what the key idea of this proof is. The key idea is to build a Floer theory invariant, the positive symplectic cohomology. This is a Z-graded invariant, and to produce an isomorphism to the ordinary cohomology. Now you might say, why go through the trouble of computing a very complicated Floer theory invariant if you're just going to recover the ordinary cohomology? so fair point. So the reason for that is that the generators at the chain level of this symplectic homology, the generators are are labeled in a very natural way by the conjugacy classes of the group, which is the thing that's somewhat mysterious about this statement. You know, why should the generators of the homology be labeled by conjugacy classes? And that's because the orbits that generate the Hamiltonian orbits that generate this group at the chain level are Hamiltonian orbits in Y that are precisely related to eigenvectors of this group action on Cn. And moreover, we can explicitly calculate the Conley-Zender index of these orbits, and apart from this degree shift here, they recover exactly the age grading of G. So in the next slide, I'm going to try and explain what these orbits xg are. Okay, so first, let's do as a warm-up. Let's just consider first Hamiltonian flows in Cn mod G. So I hope this slide is somewhat more comprehensible than the other slides. So we're just looking at Cn mod G. We do a little averaging trick, so we can assume that our finite group is actually an SUN. This ensures that all of our symplectic data, symplectic form, Reb fields, and all these things, they descend very nicely to the quotient. And we look at the C star action on Cn, which is just multiplication of all the coordinates by an element of C star. And this action descends to Cn mod G. And inside this C star action, we have an S1 that acts just by rotation. And this is generated by the usual Hamiltonian flow for our favorite Hamiltonian, which is just the norm squared. Now, when we do Floer theory, we don't want to. We look at one periodic orbits of Hamiltonian flows. We don't want to use this Hamiltonian because then everything will give rise to an orbit. What we do is instead we build a Hamiltonian that grows as we go off to infinity. So here's a picture of. So here's our singularity. Here's our isolated singularity. This is 0. Here we have Cn mod G, and then if we fix a value of the norm, we get this link of the singularity we mentioned in the previous talk. So let's call this slice S. So this is just a sphere modulo G. And we pick a Hamiltonian that slowly grows from 0 up to a multiple of this h. So here we say k times h. So here the flow is you rotate k times. And so here for technical reasons you don't want orbits at infinity. So actually we'll flow by k plus epsilon, and here k plus epsilon times. So maybe I should clean this up slightly. Okay. K plus epsilon times. Okay. So the flow here starts off. So here the flow is very slow. Eventually the flow will reach. So here so let me just write this z. So here the flow, this will be e to the I a t times z. And so because we're making this Hamiltonian hk grow, its rotation by some sort of speed a, and the speed a increases all the way to k plus epsilon at infinity. And so the question is, when do we actually get a closed orbit in this quotient? And so in order to get a closed orbit in the quotient, what we need is we need this e to the I after time 1. After time 1, this is e to the I a z. We want e to the I a z to be the same as z viewed in the quotient. So that means that e to the I a z is g times z for some element of the group G. And if you look at this equation, this is exactly saying that z in Cn is an eigenvector for G with eigenvalue e to the I a. And conversely, if you give me an eigenvector of Cn with this eigenvalue, you can write down this orbit xg, which is this xg that I mentioned before. This xg is just the flow with this particular speed, and the endpoint is identified with the original point because of the element g. Okay, so now if we assume that we have an isolated singularity, so g acts freely away from 0, then once you tell me once you tell me how much you're flowing, this e to the ia, you uniquely recover the element g. Yeah, so this is the same as saying g twiddle inverse g of z is z. So you recover g because you're not allowed to have fixed points because of the freeness assumption, and so so this is a particularly nice setup. If you were in the non-isolated case, life becomes harder because because elements z of your in the singular strata have stabilizers, and so this correspondence has to be slightly corrected because of stabilizer elements. Okay, so anyway, in the isolated case, then our orbits are labeled precisely by these elements of the group G, and in fact, upon closer inspection, because we're actually working in the quotient, we don't care. There's no difference between z and hz. If you change the point z to hz, then actually this element G will change exactly by conjugation. So actually, the thing you care about is not so much G, but actually the conjugacy class of G. And so you see that the Hamiltonian orbits are precisely labeled by conjugacy classes. Okay, so now let's look at what happens on the resolution Y. So on the resolution, on the Kreppen resolution Y, this is a fact of these Kreppen resolutions is that this diagonal C star action actually lifts to Y. So the projection map is C star equivariant. And what we do is this answers a question in the previous talk. So because we assume that our resolutions Y are quasi-projective, they have a Kähler form. So they have a symplectic form. And then by playing around with these symplectic forms, one can ensure that in fact we can build a Kähler form on Y, which agrees under projection with the Kähler form on X at infinity, and then sort of slightly modified near the exceptional locus. And using that Kähler form, and then by an averaging trick, we can just ensure also that the S1 is also a Hamiltonian action also upstairs, and therefore given by some Hamiltonian function little h. So I'm sort of abusing notation by using the same letter here. Okay, and so again as before, when you do the Floer theory, to do the Floer theory, you look at a sequence of Hamiltonians that grow more and more at infinity. So you're sort of rotating more and more at infinity, and you want to take a limit of these Hamiltonian Floer cohomologies as you make this rotation faster and faster at infinity. And which Hamiltonians you pick does not actually matter by invariance. You could pick these Hamiltonians that grow. Or you could also pick Hamiltonians that are just linear, so k plus epsilon. So actually, sort of without a sort of cutoff, here. Okay. So I won't say much about Floer theory, so that the talk doesn't end with just talking about Floer theory. So I'll just say two things. The generators of this Floer cohomology are the one-periodic orbits, and the differential counts infinite cylinders that satisfy an elliptic PDE called Floer's equation, which is Cauchy-Riemann equations perturbed by the gradient of the Hamiltonian. And for the purpose of this talk, the differential will not actually matter so much. The key thing is that the generators at the chain level are the one-periodic orbits. Okay, so now because our two spaces, because we're assuming we're in the isolated singularity case, this is the picture we have in mind. Here's Y, here's E, the exceptional locus over the singular point. Here's our singular space, and this is Cn mod G. So this is X. So the two spaces coincide away from the exceptional locus, and so here we have these orbits xg, which precisely lift to orbits, the same orbits upstairs. Okay, and in the non-isolated case, the hard thing about life is that if you have these in the singular strata, then here you will have multiple lifts, and that's related to the fact that you have stabilizers, as I mentioned before when we talked about the eigenvectors. Okay, so now the first key result is that the symplectic cohomology of the Kreppen resolution is actually 0. And one way to prove it is sort of mimicking some earlier work of mine, but actually even simpler, you can just think back at sort of origins of symplectic cohomology when one computed the symplectic cohomology of Cn. So what happens for Cn is you take your favorite Hamiltonian half of z squared, you put a generic coefficient here. Here you have the flow of this S1 action, but the orbit never closes up. You never have one periodic orbits. The only one periodic orbit is at the origin. And then you ask yourself, what's the grading of this orbit? And the Conley-Zender index grading remembers how fast the flow is rotating nearby. So the steeper this becomes, the more negative the Conley-Zender index becomes. And so the only generator we have at 0, it has arbitrarily negative index. And so in this limit, in any given index, there's no generator, so the symplectic cohomology vanishes. The same argument applies here. By picking these linear Hamiltonians rather than this one, for generic coefficients, the only orbits are constant orbits in E, and then you check that, again, their Conley-Zender indices go off to negative infinity. And so, again, symplectic cohomology is 0. Okay, now you might say this is bad news. Fair point again. But actually, it's good news for us, because here, if you use these Hamiltonians, near here, your Hamiltonian is almost 0. So actually, your Floer complex here is just like a Morse complex. It's a Morse spot complex for this. So this calculates the cohomology of Y. The whole cohomology of Y is actually by sort of deformation retraction lives in the cohomology of E. So those orbits give you the cohomology of Y. And therefore, the quotient complex, so if you only do the Floer theory for orbits that are away from E, the quotient complex should give you a cohomology that's the same as the ordinary cohomology, which is what we want to achieve. And so what one does is, so what we do is we check that what works in the exact setting also works in this non-exact setting. So this goes back to work of Viterbo, is that we can build a filtration on this chain complex that ensures that for a small slope Hamiltonian, so in other words, near here, the Floer complex just gives you is just a Morse complex for Y, and so we get a long exact sequence that maps the ordinary cohomology into the full symplectic cohomology, and then this SH plus is just the cohomology of the quotient complex that you got from quotienting out this subcomplex, the Morse subcomplex. And because SH was 0, the long exact sequence tells you that indeed SH plus recovers ordinary cohomology up to this slight degree shift. Okay. Now the next ingredient is that the filtration also tells you that there's you can also build a more spot spectral sequence. So what does that mean? It's here when you have Floer trajectories, so these are cylinders that move along, we check. Again, this is something that sort of is known in the exact setting, but we check that we show that you can also do this in this non-exact setting, is that these Floer cylinders, that if you move away from this slice, then you must consume energy. And the more energy you consume, those things should contribute to higher and higher differentials of your spectral sequence. So the lowest order differential in this spectral sequence is the local Floer cohomology, which of all the trajectories that live precisely in this slice. And the local Floer cohomology of what lives in this slice is actually just the ordinary cohomology. The ordinary cohomology of the moduli space of one periodic orbits that you have in this slice. And so what you get is, if we abbreviate, so apologies for all this notation, but let's abbreviate by this. O is for orbit. G, bold G, is the conjugacy class for G. A is for this the eigenvalue, so the phase of the eigenvalue. So this tells you the moduli space of one orbits associated to the conjugacy class with a particular eigenvalue. So for each slice, you have a particular speed at which you're rotating, and then that gives you, and here you have some submanifold of initial points that gives you that give you closed orbits. And this is the cohomology that you get from your local Floer cohomology. And as we saw also in the previous talk, one has to be careful because the grading has to be shifted, and the shift is just the Conley-Zender index of these one-periodic orbits, and that's because you have to keep track of how the Hamiltonian flow is slightly away in the normal direction, and so there's a shift in the index. Okay, and then this more spectral sequence converges. So this is just the Floer cohomologies of the slices. And then higher and higher differentials look at other sort of longer Floer trajectories, and eventually the spectral sequence converges to the positive symplectic cohomology. Okay, and now so what we sort of claim is that this positive symplectic cohomology is precisely generated by looking at you look at these for each conjugacy class. You look at the smallest eigen for each. So this is let's say this closes up and this is equal to G times Z. You look at the smallest eigenvalue that occurs for G. So that's the minimal eigenvalue, and then you have this manifold of orbits here. And because you're doing a more spot theory, you look at the maximum of that manifold, and the maximum of that manifold should be is the generator that survives to the symplectic cohomology. So that's what we claim. And for our purposes, we actually only needed a slightly weaker statement. So we proved a slightly weaker statement, but we believe this is, in all examples, this is what happens. Okay, so this is very abstract. So I think the next slide is finally an example. So if I've lost you, here's a sort of simple case. So we're looking again at this example here, C2 mod plus or minus identity. And remember here, this is the cotangent model of CP1. So what happens in this case? So here's our picture. This is a picture downstairs, and upstairs this 0 has been replaced by something more complicated, by CP1. So here are our slices, which are these spheres. Okay, and so these are the slices, which are S5 mod plus or minus identity. S3 plus or minus identity, and so at the beginning the flow is so we're using this Hamiltonian here. At the beginning the flow is very small, so the orbit doesn't close up, so you just get an open orbit. Eventually the flow is fast enough that it goes all the way to the antipodal point. So here is Z, and then here's the antipodal point minus identity Z, and these 2 points are identified modulo plus or minus identity. So this is the first closed one periodic orbit. Eventually this flow is very fast and it goes all the way around, so you get a full great circle in S3. So here Z, so here Z is the same as plus identity times Z. So these are the elements G that tell you that you close up. And then the next slice you'll go around 1.5 times, 1.5 times, and so on. So here you get back to minus identity times Z, and so on. And because of the symmetry of the problem, in fact, it didn't matter what initial point I picked. And so here what we get is our manifold of initial points is exactly S3 modulo plus or minus 1, which is an RP3. So here we get the cohomology of RP3, and then here again we get the cohomology of RP3, and so on. But we have to remember that the degrees get shifted. So in fact, it turns out that here the degrees would be in degree 0 and 3, and here the shifts are, this is plus 1 and minus 2, and minus 1 and minus 1 and minus 4, and so on. So that's so all of these numbers in this more spot spectral sequence, they represent a copy of the base field, and I've written down the degree where it lives. And now here, so all of the colored stuff is SH plus. The blue ones are the ones that go around and that end up at minus identity of the initial point. The red ones are the ones that do full circle, so they're the orbits that actually lift to closed orbits in the sphere. And then here in brackets I put the cohomology of what lives over 0, which is just this 0 section, CP1, which has generators in degree 0 and 2. And we know that SH star without the plus, it vanishes. So this chain complex has to be acyclic. Everything has to kill each other off. So these are where the differentials have to be. And the differential increases grading by 1. So here you see all the arrows, everything gets killed. And so if we do SH plus, the quotient complex, which means we ignore the Morse complex that gives you the cohomology of Y, the two things that survive are these two, this +1 and -1, which is precisely the first orbit, the first closed orbit that we saw, and this first closed orbit that we saw, and they are the maxima of these two Morse spot manifolds of orbits. Okay, and now let's check that the age grading is all right. So here the half-grade circle, which is the first one that we saw, that lives in SH1, right? And then here we have this shift in degree. So we expect an H2 generator in Y. So the age should be 1, so 2 times 1. And indeed, if you look at minus the identity, it has eigenvalues -1, -1. The phases are pi and pi. That they add up the phases, you get 2 pi divided by 2 pi is 1. So that's the correct age. And then for the full grade circle, that's the identity map. And the identity map has eigenvalues 1 and 1. The phases are 0, so age 0, and double of 0 is 0. So here you get H0, and that's indeed this generator in degree -1, which is this one here. Okay, very good. So there's two more slides to go. So here we slightly, this is obviously the simplest example, and we sort of cheated because we knew exactly the cohomology of Y. Now the cohomology of Y is a thing that we're supposed to pretend that we don't know. So we want to now pretend that imagine we didn't know this. Now this is a simple example where even if you didn't know this, you would see that these two are the only ones that can survive. But imagine you're in a more complicated quotient. You would have these, lots of orbits appearing for lots of different elements of your group, and so there could be some maps here that you have no idea what might happen, and so we need a workaround, and the workaround is unfortunately to use a slightly more complicated Floer invariant, which is the equivariant S1 equivariant Floer cohomology, and surprisingly that turns out to simplify the story. So now here life gets a little difficult, and I have to make one sort of very technical remark, but it's somehow crucial. It's over how the coefficients work in S1 equivariant in the S1 equivariant Floer theory. So if you're doing ordinary symplectic cohomology, you work over what's called a Novikov field, and you can just think of that as a Laurent series in a formal variable t, and the variable t keeps track of energy. So this is just like in quantum cohomology. Now, when you're doing S1 equivariant symplectic cohomology, there's various choices of coefficients, and actually the choice is quite important. And for the purposes of this work, we use this module F, which unfortunately I chose F, which is not so good because it makes you think it's a field. So if I say field, I apologize. It's a module, and it's a module over the series in this formal variable u. So when you do S1 equivariant theory, you have a formal variable u in degree 2, which is the generator of the cohomology of CP infinity, which is the classifying space of S1. So you have this new formal variable u. And here you're looking at Laurent series over this formal variable u, working over this Novikov field, whatever it is, and you're killing off all the positive series in u. So a typical representative of an element, right, remember Laurent series, they have only finitely many terms with negative powers of u. So you've got these finitely many terms with negative powers of u, and all the ones with strictly positive powers of u, you've quotiented out, so you can just ignore those. And now, just to give you an idea of why we're doing this, here we're doing really more like a homology version of S1 equivariant theory, and here, so you're thinking of this as this U generates really the homology of CP infinity, and the sort of cup product by the cohomology of CP infinities is a nilpotent action. So if you keep multiplying by U, eventually you make these powers positive and they die. So the action by U is nilpotent. So it's more like a homology of CP infinity rather than a cohomology of CP infinity, which would be a polynomial ring in U. So there's this issue that sometimes you want Floer theory to behave homologically, sometimes you want Floer theory to behave cohomologically. So here we're making it behave homologically, which is why we're using these very strange coefficients. Okay, and I'll just say that the Floer differential involves the usual differential plus some correction terms that involve higher and higher powers of U, but we don't really care so much about the differential for this talk. Now, as before, the full S1 equivariant symplectic homology vanishes, and you can either argue by the same reasons, because the Conley-Zender indices go off to negative infinity, or you can just say that this is a consequence of the fact that of a spectral sequence argument, because SH is 0. In any case, so as before, SH is 0, and so only the plus part. So and that's good because we care about the plus part, the orbits away from the exceptional divisor, and the plus part again up to this grading shift recovers the ordinary cohomology. And this time it's the ordinary S1 equivariant cohomology. The S1 acts on loops, but when you think of the Morse setting, you have just critical points, so the S1 action is trivial. So when you have a trivial S1 action, the S1 equivariant cohomology is just the usual cohomology, except that you might have to change the coefficients. So so we just get the ordinary cohomology, except that now we're using this funky module of coefficients. Okay. In particular, what this tells us that ESH plus is a free sum of these funky modules, and they are supported in the degrees that you would expect the ordinary cohomology to be supported in. Okay, now how does the Morse spot spectral sequence change? So remember, we had to do we did the cohomologies of these Morse spot manifolds of orbits in the various slices. Now instead of the ordinary cohomology, we have to do the S1 equivariant cohomology, and the S1 equivariant cohomology of these slices now corresponds to cohomologies of CPK. So let me explain this in this example here. So what would happen here if you do S1 equivariant cohomology? So first of all, we're working over characteristic 0, so all torsion phenomena can be ignored. So this S1 action on here, you can just, over characteristic 0, you can pretend that this is S3, and then you're just acting by S1, and it's acting freely, and so the S1 equivariance cohomology of S3 is actually just the cohomology of the quotient of S3 modulo this free action of S1. So S3 mod S1 is just CP1. And so instead of getting cohomology of RP3, we now get, the new thing is that we now get instead cohomology of CP1. And the difference here is that here these are in degree 0 and 3, here the generators are in degree 0 and 2, which have the same parity. And so this miracle happens that once you look at the Morse spot spectral sequence, these top generators, they still have the same Conley-Zender index. And here you see, in these columns, you see the difference is always a degree shift by 3, because this is in degree 0 and 3. Now the degree shift will be 2. And so this bottom row gets actually lifted up by 1 in degree. So this bottom row is now up by 1 in degree. And so they're all now in odd degree. And because they're all in odd degree and the differentials increase grading by 1, there are no differentials. So it's a miracle that all Floer differentials are 0. So usually you can never calculate Floer cohomology unless you're in a situation where either topology tells you that there are no differentials or the grading tells you there are no differentials. And that's exactly the setting that happens also in general. All these generators have the same parity, which is also what Miguel mentioned in his previous talk, that you have this sort of parity miracle that happens for generators. And so the Morse spot spectral sequence collapses immediately. You don't need to worry about differentials, and you just get these cohomologies of these Morse spot manifolds of orbits with a degree shift. Now, in this case, these quotients, one thing that we check is that these modular spaces of orbits, modulo by S1, they're actually always finite quotients of CPK, and so over characteristic 0, that's the same as the cohomology of CPK, and so so it's actually a very simple cohomology. Now, the final ingredient is we didn't really want S1 equivariant SH plus. We wanted the non-equivariant theory. And so the final ingredient is how can we recover the ordinary one? Now, let's look at, again, these columns. So remember here, these things, they all correspond to copies of the Novikov field K in that particular grading. But we also know from this result, from the Long's sequence, that we should get a direct sum of copies of this funky module F. And so all these copies of K should be arranging into a copy of F, right? So this F is, where shall I go? Here. So you know, F is you've got a copy of K U0 plus as a vector space over K. This is KU0, KU minus 1, KU minus 2, and so on. So it's a polynomial. as a vector space is the same as the polynomial ring in U inverse. And so, this is in degree 0, in degree -2, degree -4, and so on. And so you see that these copies, these blue things, they always jump down by 2. So here they just jumps down by 2 because this vertical thing is the cohomology of CP1. But notice this miracle that from here to here, when you have this iterate, this also jumps by 2. Then from -5 to -7 you jump by 2. From -9 to -11 you jump by 2. So you have this phenomenon that these blue columns, they arrange themselves exactly into a sum of copies of K. And with degree shifts by these powers of U inverse. So that's this thing here. So you see you've got these copies of K, and they give you exactly this funky module F in degree -1. And then similarly for the red columns as well, they arrange themselves perfectly into a copy of F. Okay, and the final ingredient is the symplectic Gisin sequence of Bourgeois and Oancher. And it tells you, and it gives you a long exact sequence, and often you have a chance at recovering the non-equivariant symplectic homology if you know a lot about the S1 equivariant symplectic homology and some things about these maps. So just to put this long exact sequence a little bit into context, let me tell you what the classical theory is briefly about a classical Gisin sequence. So in the classical case, what you have is you're looking at just a manifold M. You have an S1 bundle E. There's a cap product action by the Euler class of this bundle, which shifts degree down by 2. And of course, you've got the push-forward map from E to M. And this gives you a long exact sequence with the connecting map being just roughly pre-images of cycles. Now, if you want to know what the analog is in Floer theory, in a sort of hand-wavy way, you try to replace this by loop spaces and see what happens. And now we're doing the equivariance theory, so we're looking at loop space cross the ES1 space, which is S infinity, and then modulo the S1 action gives me M. So we're considering the free loop space cross S infinity and the free loop space cross S infinity modulo the S1 action. So here this M gives us, because this is the Borel, this is the, it's called Borel model for the equivariant S1 equivariant symplectic S1 equivariant cohomology. So this thing here just gives you the equivariant cohomology of the loop space. And then here, this S infinity is contractible, so this E gets replaced by the loop space. So you see you have this long exact sequence, hand-wavy thing. You replace homology by symplectic homology, and you can put plus decorations if you like. And you see that it sort of fits with the sequence. And here on homology of the degree shifts down by 2. Here the homology shifts up by 2. And in fact, this map here is multiplication by this formal generator U in degree 2. Okay, so now what happens in our case? Now we showed that the spectral sequence collapses in general, and everything is in the same parity. Everything is in odd degrees. So actually, this long exact sequence breaks up into these exact sequences where here this 0 corresponds to even degree ESH plus, which doesn't exist. And here the map, this connecting map here, sorry, this central map here is multiplication by U. Okay, and then you just need to ask yourself, so this is 0, this is -1, this is -2, and here's another copy of F. And how does multiplication by U act? This is multiplication by U. So multiplication by U on copies of F is always surjective. And so that means that this map here is always surjective. So that immediately tells you there's no even symplectic SH plus, which is good, because once we shift by 1, that should be the odd cohomology of Y, which by the McKay correspondence we expect it to be 0. Indeed, we get 0. And then the other thing it tells us is it tells us exactly what the odd SH plus is. It's the kernel of this map. It's the kernel of this map U. So what's the thing that survives? It's the stuff with the U to the 0 stuff. And the U to the 0 stuff in our example is exactly these first two guys, which are exactly these two orbits, the first two orbits that appear for the minimal eigenvalues for the two conjugacy classes. And the final ingredient is at some point you need to we need to count the number of generators, and this is the thing that I can't do in the talk for time reasons. And but this is something that you can now do just on on this contact manifold here, S2, where are you? S2n minus 1 mod G. You just have to calculate Conley-Zender indices for your favorite Hamiltonian flow, And so you just have to write down how you define the Conley-Zender index and calculate. And you see that the number of generators is exactly, so the rank is the number of copies of F that you get by arranging these columns is exactly the number of conjugacy classes. And the Conley-Zender index precisely recovers the age grading. And so this in the end then finishes off the proof, because you now know exactly the number of the rank of these SH plus groups. So in our example, these were these two top copies of K that gave us the two cohomologies. Great. So that's the end of it.